At this time, I'm pleased to introduce Nate Soares, a research fellow in the Machine Intelligence Institute. He works on foundational problems relevant to the creation of general intelligence, including decision theory, goal stability, corrugability, and value loading. Today, he will present a talk titled, "Why Ain't You Rich? Why Our Current Understanding of Rational Choice Isn't Good Enough for Superintelligence." Please take a moment to silence your electronic devices. Thank you, and enjoy.
Good afternoon. My name is Nate Soares. I'm here to present Why Ain't You Rich? You've already heard the title. I work at the Machine Intelligence Research Institute. We do foundational research to ensure that smarter than human artificial intelligence has a positive impact. That is the official slogan. I have a more informal version that I like, which is we're trying to figure out how to ensure that a superintelligence would have a beneficial impact. And we're trying to figure that out before someone turns one on. I've been invited here to give a more technical talk. The keynote talk will give a bit more of a motivation behind why these are important things. I'm going to dive into some of the technical details of why we shouldn't necessarily expect that we get good behavior from superintelligence by default. Let's get this slide out of the way early. There will not be a Q&A. If you have questions, I'm using Hot Seat. The number is hopefully readable. This will be there throughout the talk. They will come to my tablet. I will ostensibly see them and answer them. We'll see if this works. So like I said, I'm not going to motivate why we need to worry too much. That'll be motivated later. But since we're at the Dawn of Doom conference, I will assume that you're familiar with the idea that we might one day build something that is smarter than us. And also with the idea that it is our smarts and not our strength or our speed that gives us as humans control over the future of the planet. It is our intelligence that allows us to light up the night. And if we build something smarter than us, then just as we control the future much more than do the great apes, something far smarter than humans might control the future far more than we do. Finally, I'm going to assume that you're familiar with the idea of an intelligence explosion, that we may one day make a machine that is better than we are at intellectual tasks, including the generation of smart machines. And that if this happens, and they make smarter machines, and they make smarter machines, and so on, it may quickly lead to an intelligence that is far, far smarter than any human, that is capable of having an extraordinary impact on the future. If we want to ensure that that impact is good, it depends entirely upon how well we can specify the initial machine, the thing that starts the intelligence explosion. There are a number of open problems when considering how to build a superintelligence. Things that we don't yet understand in order to make a superintelligence that we can ensure would have a beneficial impact. For example, we don't yet understand how to build a goal-oriented system that helps you correct its goals instead of manipulating or deceiving you in attempts to defend its flaws. We don't yet understand what sorts of processes can successfully convey the complex notion of value to an artificial intelligence. And today I'm going to talk about one specific subproblem in the space of decision theory. Now you may wonder, why do we need to worry about decision theory when ensuring the safety of an artificial intelligence? Decision theory is the study of how to make appropriate decisions. And it may seem naively that we can trust this to the superintelligence. If you have some smart system that's making itself much smarter, surely it figures out how to make good decisions, right? Like, if you have something that makes bad decisions, the label superintelligence probably doesn't apply. The reason that we worry about decision theory is it seems possible for decision theories to be both unstable, in the sense that if you built an AI using that decision theory, it would stop using that decision theory, and unsatisfactory in the sense that there are some decision theories which have blind spots that they cannot fix. These problems both stem from the question of how do you reason counterfactually? When you're choosing between actions, there are a bunch of actions you could do, and there's only one that you're going to do. When you're evaluating which to take, you have to reason about what would happen if you took actions that you're not going to take. This is usually fairly easy. We have algorithms that do this pretty well, but there's some subtle cases where it's hard, and those subtle cases can lead to really bad behavior sometimes. That will be the discussion of this talk. I'll illustrate some of these failings. As an example, humans are usually pretty good at counterfactual reasoning. We're usually pretty good at evaluating what would happen if we did something, even if we're not going to do it. But there are times when we get really bad at it. This is actually where decision theory comes from. It's not an AI field originally. It's trying to figure out how humans make good decisions, because sometimes humans make really bad choices. Surprising to everybody, I know. An example of humans making bad choices is there are people who believe in palmistry, that you can get your palm read and it tells you something about your fortune, and then get palm surgery in order to alter their palms and thereby change their fate. I have spared you the pictures of palm surgeries because they give me the heebie-jeebies. But people sometimes make bad choices. Now, I'm actually a little bit sympathetic with people who get palm surgery in order to alter their fate. If you could convince me that palmistry worked, the first thing I would do is check whether or not I could change my palm in order to change my fate. It's like step one. But most people who think palmistry works probably have a world model that looks a bit more like this. This is what's known as a causal graph. The nodes are events. The arrows represent causality. And throughout this talk, the dashed gray circles will be the action node. This is where your choice happens. It's where you make your decision. And the dark diamond will be the payoff node, which describes the outcome. So this graph describes a belief about the world where there is some destiny thing which affects both your fate and the lines on your palm. And the lines on your palm can be read by a fortune teller who will tell you a fortune. And surgery can change the lines on your palm. But the fortune that you get doesn't change your fate. If you change your palm, you can change your fortune, but you won't change your fate. And people might reason, hey, everyone who gets a good fortune has good outcomes. But if they get the palm surgery, they're failing to reason that the palm surgery does not cause their fate to change, even if palmistry works, for reasons beyond palmistry not working. This leads us to the prescription of causal decision theory, which is the modern standard decision theory, and prescribes choosing actions based only upon the causal outcome, the causal effect that your action has. There are many ways of formalizing causal decision theory. I should also note that regardless of whether or not you think you're using a decision theory, if your counterfactual reasoning, if the way you reason about what would happen is causal, then you implicitly are using causal decision theory. And in fact, most narrow AI today, economics, statistics, they all do causal counterfactual reasoning and thereby are implicitly using causal decision theory. I'm going to abbreviate causal decision theory as CDT throughout the talk because it's kind of a mouthful. And there are many ways to formalize it. This is the formalization in the language of causal graphs, which is particularly good for presentations because I can have pretty graphs. It's a pretty simple algorithm. You identify your action node. You identify all the actions that you can take. You identify your payoff node. And then you go through each action, and you consider causally how the graph would be affected if instead of having your action node be like the decision process that is you, you instead have your action node be a simple function that returns the action under consideration. So you overwrite your action node in like your model of the action node. You don't actually overwrite yourself. You overwrite your model of the action node with a function that always returns the action you're considering. You like see how this affects the causal graph. You take the action with the best outcome. The thing to pay attention to here is that causal counterfactual reasoning involves evaluating your actions only based on what would happen if instead of being you were some simple function that did the action under consideration. This usually works really well. This is why it's standard in economics, statistics, AI, so on. There's like a famous problem that was kind of hard for decision theory back in the day where CDT was invented to solve it, which is like you have a gene that causes both liking gum and stomach ulcers. And the decision theories of the day would say, well, if I chew gum, I'll probably have ulcers because they can't model this confounding variable of the gene. CDT can handle this. It works great, but sometimes it fails. And those failures are what we're going to look at today because they make CDT, our modern understanding of a good decision theory, inadequate for use in a superintelligence, as we'll see. In order to explain the failure, I'm going to use a simple game throughout the rest of the talk. This game is called the token trade. It is a two-player game, and it works like this. I take the first player, I put them in a red room, and I hand them a green token. I take the second player, I put them in a green room, and I hand them a red token. And then each player must decide, without communicating, whether or not to give their token away or to keep it. After they have decided, if they have given their token away, I take the tokens that they gave and I give them to the other player. And then they get to cash out their tokens. The red player gets $200 for the red token and $100 for the green token. The green player gets $200 for the green token and $100 for the red token. So for example, if the green player gives their token away and the red player keeps their token, then the green player gets nothing while the red player gets $300. I'm going to give you a few seconds to make sure that you've internalized this game. It's just a variant of the prisoner's dilemma while I go pick up the fallen tablet. So this is the token trade. And we're going to consider a special variant of the token trade called the mirror token trade. In the mirror token trade, an opponent is played against a perfect copy of themselves. Now, to avoid questions about determinism and whether or not people can distinguish red from green, we're going to assume that the player is a deterministic algorithm. It's a deterministic algorithm that is going to be put in this environment and has to reason in some fashion and decide what to do. And we're going to assume that it's red-green colorblind. So this is a perfectly symmetric game with a deterministic program that's playing against a perfect copy of itself. So I'm going to take some template, the source code of the program. I'm going to instantiate two copies. And I'm going to put them in a token trade. And they each have to decide whether or not to keep their token or give their token away. So consider the agent that wakes up in the red room. They are this give node. That's their decision node. What should they decide to do? Clearly, they should decide to trade their token. Because if they keep their token, then so will the opponent, and they'll both get $100. But if they trade their token, then so will the opponent, and they both get $200. They should give their token away. CDT does not do this. Because CDT only reasons about the causal implications of its actions. And the other player, by the time a CDT agent is making its decision, the other player is causally distinct. If you are in this situation and you give your token, then so will they, but it's not because you've caused them to. It's because of a logical relation between you and them. CDT can't model these. When CDT builds this environment, it assumes that everything, when it builds this model of the world, it assumes that everything which is causally disconnected from it is logically independent from it. And so it thinks that there's some probability that the other player will give their token. And it says, no matter what the probability is that they give their token, I get $100 more if I keep my token. And so it keeps its token. Drastic failures, I know. It loses $100. But what went wrong? Now, some philosophers will argue that what went wrong is that this is an unfair game. There's mind reading involved. There's a literal perfect copy, which is like we don't have literal perfect copies of deciding agents generally. And they'll say that it is in fact rational to keep your token, because no matter what they do, you get $100 more for keeping your token. In response, I have a couple of responses. The first is that this game is fair enough for me. If you put me in a token trade against someone who's guaranteed to do the same thing that I do, then I will trade my token, and I will walk away with $200. And if you protest that this is irrational, and you keep your token, then you will walk away with the $100. Why ain't you rich? Presumably because your adherence to what you think is rational is worth more than $100 to you. But I digress. My second objection is that the real failure that's happening here is that CDT is unable to model logical dependence in these nodes. When the opponent's action is going to be the same as yours, it doesn't make sense to reason like, no matter what they do, I get $100 more. This sort of reasoning, when you say no matter what the probability is that they are going to keep their token, this has already broken your counterfactual, because you're assuming that they can be distinct from you, when in fact you're logically the same. So the remaining objection is that this isn't that big a deal. This only happens when someone can read your mind, or when someone can perfectly predict what you're going to do. There are actually a number of these scenarios in decision theory. They're known as Newcomb-like problems, after some guy Newcomb who went and pissed off a lot of decision theorists by giving them problems where CDT did poorly. And one of the common objections is that Newcomb-like problems don't matter. I'm going to argue exactly the opposite. Newcomb-like problems are the norm. These scenarios occur whenever someone else in the environment is basing their action on how they think you will act. You are causally disconnected from that, right? Like when you are making your choice, you are causally disconnected from their reasoning about your choice. But you're still logically connected to because they're reasoning about you. And in fact, any scenario where other people in the environment are reasoning about how you reason, even if it's not perfect knowledge, you get one of these Newcomb-like scenarios. And in fact, these are exactly the types of scenarios that humans find themselves in all of the time. When you ask someone out on a date, you don't immediately invite them to your house. You go meet in a public place and get to know each other, because you want to understand more about whether or not they're a trustworthy person. And indeed, evolution has supplied us with huge amounts of tools to make immediate, split-second first impressions, to get an idea for how other people reason. And we never make big decisions with someone before getting to know them. We have lots of tools to figure out whether someone's trustworthy. Almost everything in real-life scenarios is a Newcomb-like problem where someone else is reasoning about how you reason, even though you're causally disconnected. And an AI would not be exempt from this fact. In fact, an AI would be even more susceptible to Newcomb-like scenarios, because an AI would be interacting with the people who literally wrote its source code. It doesn't get much better than this in terms of knowing how the other person or how the other agent reasons. Which means that if you built a superintelligence, or something intended to one day become superintelligent, if you built an agent that could self-modify, that used causal decision theory, it would stop using causal decision theory. In our token trade example, if you take a self-modifying AI that knows it uses CDT, and you tell it that you're going to play it in a token trade against itself, and you give it one chance to self-modify, it will reason as follows. I'm about to be the dashed white circle. also the second white square, but one at a time. If I remain a causal reasoner, I will get $100. If I change myself to no longer be a causal reasoner, I will get $200. Therefore, it will change itself to no longer be a causal reasoner because it gets more money. This is kind of a red flag. If we built something that used the modern academic standard decision theory, it would immediately stop using the modern standard academic decision theory. And this might seem okay because it seems to be correcting the error, right? When we tell it it's going to face a token trade, it self-modifies to succeed in the mirror token trade. But in fact, it won't fix all of its problems. We have seen that if it faced a mirror token trade, if it knew it was going to face a mirror token trade in the future, it would self-modify to win in the mirror token trade. This is a general property of CDT. In any Newcomb-like scenario that starts in the agent's future, it will self-modify to essentially pre-commit to do well on all those scenarios. It can do blanket pre-commitment, fix all future Newcomb-like scenarios. But if it ever finds itself in a Newcomb-like problem that it thinks began in its past, then it reasons like the CDT agent that's already in the token trade. And we know that it fails here. It may know, when it's in the Newcomb-like scenario that began in the past, that if it had a chance to pre-commit, it would have pre-committed. But it thinks it's too late. It thinks that it's already causally distinct from the copy of itself, or the thing that's reasoning about it, or the thing that works kind of like it. And it thinks it's too late to get the money. It has this independent probability that they're going to do their thing. And it knows that in the token trade scenario, if it considers self-modifying to trade its token, to give its token away, it would conclude that if it self-modifies to give its token away, it can't guarantee that the copy of itself was self-modified to give the token away, for the same reason that CDT failed in the first place. And so it would continue to fail on any Newcomb-like scenario that began in its past. It can't retro-commit. Now, this may seem fine. It fixes all problems in all scenarios that start in the future. It just continues to fail on problems that started in its past. Maybe this is okay. Because after all, how likely is it that there will be Newcomb-like scenarios that began in the agent's past after it has an opportunity to self-modify? And the answer, unfortunately, is lots. Anyone who has a copy of the agent's original source code has the ability, post facto, to put the agent into a Newcomb-like scenario that began in its past. I know we've gotten pretty abstract here, so I'm gonna bring this down to earth a bit with a ridiculous story. So we have this AI, which was a CDT AI that is self-modified to succeed in all Newcomb-like scenarios that it thinks begin in its future. And then we have the bad guys who want to gain control of this AI. The bad guys have the capability to build a bomb that would hurt both them and the AI if it goes off, such that the bomb can only be diffused if the AI comes under their control. This way they can't be coerced into diffusing it. Once they make the bomb, the only way for it to be diffused is the AI to come under their control. They're also very cautious blackmailers. They will only build this bomb if they know that the AI will give in. They really don't want to blow themselves up. Unfortunately for them, unfortunately for the AI, they have a copy of the AI's original source. So they can run it, and they can check whether or not it gives into the blackmail before building their bomb. Now, the AI knows all this. It knows that there are bad guys that can build a bomb, have its source code, and will only build the bomb if they know it gives into blackmail. The AI knows that they're simulating it right now. What we would like the AI to do is reason as follows. If it self-modifies in real life to not pay the blackmail in real life, it self-modifies so that if they do build the bomb, it will let the bomb go off. If the AI does this in real life, then the simulated AI, which thinks it's the real AI, will also self-modify to not pay up for the same reason. The blackmailers would see this, and they would never build the bomb. But this AI was a CDT AI when it was started. And it sees that the simulation was started from the original CDT AI, and therefore concludes that it's already causally distinct from the simulation. It concludes that there must be some independent probability that the simulation will self-modify, that it cannot control because it's causally disconnected. And it further reasons that if in real life it self-modified to not pay into blackmail, the only thing that this self-modification would do would make it so that there's some scenarios where the bomb is built and everyone dies. So an AI that started out as a causal reasoner would not self-modify, would not resist the blackmail. The bad guys would see this, they would build the bomb, the AI would give in, they would take control. Now you may say, hey Nate, isn't this an entirely unrealistic pathological edge case scenario? Yes, it is. However, this scenario tells us something about our modern understanding of decision theory. We don't know what we're doing. A human understanding of decision theory, the academic standard, the thing we use in economics and statistics, the thing that's used in narrow AI today implicitly by causal counterfactual reasoning, is both unstable in the sense that if we built an AI that used that sort of reasoning, it would immediately self-modify to stop using that sort of reasoning. And it's unsatisfactory in the sense that it has flaws that it would not be motivated to fix. It already thinks that those flaws are too late to be fixed. It can't retro-commit. It's a decision theory that is broken in such a way that you can't expect it to fix those breakages itself. And while these specific scenarios here are a little wild, this shows us that we don't really have much confidence in existing decision theories. We don't have a good understanding of how to reason as if others are reasoning about you. Although that's actually a lie. We at the Machine Intelligence Research Institute, we have developed a decision theory that can handle all of the problems in this talk. It just happens to be susceptible to upgraded versions of the problems in this talk that would have been even more abstract. These problems inherently stem from the problem that we don't know what it means to do good counterfactual reasoning. If you have a decision algorithm that is deterministic and has multiple actions available to it, and you want to question what would happen if you did one of the actions that you're not going to take, this causal method of counterfactual reasoning ignores logical connections between your algorithm and other people who are reasoning about your algorithm, which generates these kind of weird scenarios that show up particularly well in edge cases, but also would show up in any situation where you're interacting with someone who reasons about how you reason. In order to solve this problem in general, we need some way of reasoning about what would happen if the program outputted something that it doesn't output. We don't have a good mathematical understanding of how to reason about these counterfactual objects. What does it mean to consider that a program does something other than what it does? What rules of math or logic are you breaking in order to get this thing to return something that it doesn't? And how does that affect your reasoning about how other people are reasoning about you? We don't know yet. This is tied into our lack of understanding about how to reason under logical uncertainty. Big open questions. Most importantly, we don't yet have an algorithm that knowably converges on a good decision-making procedure, even if we give it unlimited computing power. It seems like we might want to have one of these before we turn on something that's intended to become super intelligent or intended to have a lot of autonomy and power in the world. Let's check for questions. Y'all are boring. I'm happy to talk more. This is not the only open problem. There are actually a bunch that are just, believe it or not, harder to explain in 45 minutes. Decision theory is just one of the fields of mathematics where we don't yet have something that would knowably behave well if we put it into a superintelligence, or something intended to become superintelligent. Examples of other problems. What sort of formal reasoning system can we use to have something reason about itself with high confidence? If you're building an AI that is making self-modifications, and you want it to make lots of self-modifications without ever going wrong, it needs some method for gaining confidence in each individual self-modification that's very high. If this thing is going to make 1 billion self-modifications, then there better be much less than a 1 over 1 billion chance that each individual modification will fail. When we need this kind of confidence in jets, in spaceships, when NASA does things, when NASA writes software, we use things like theorem provers. We use formal mathematical reasoning that proves that the system is safe. But there are inherent really hard problems in formal systems proving themselves safe. You can't do this. A formal system cannot prove itself consistent. What sort of reasoning should we use to reason about similar systems that can reliably get an AI high confidence in self-modifications? We don't have one yet. Another example. We don't understand reasoning under logical uncertainty. Probability theory assumes logical omniscience. If there's a black box that takes one input to one of 3 outputs, using standard probability theory, you might not know what'll happen when you put the input in because you don't know what's in the box. And if you did know what's in the box, if you knew what machine it implemented, it's assumed that you would know exactly what would happen. But in real life, it's much more common to know exactly what's in the box. It's some complex computer program. And we just don't know what the computer program does. We don't have a good understanding of how reasoning under logical uncertainty should work. And like with decision theory, it seems possible to make approximations that are pretty good and can get you pretty powerful, but that have weird bad behavior in the limit because we don't yet understand how the good reasoning works. We also have the corrigibility problem. Any goal-oriented agent, if you give it the wrong goals, or if you give it goals that you don't like, by default, it has incentive to preserve those goals and to manipulate and deceive the programmers with intent to preserve those goals. And it seems pretty difficult to build a goal-oriented system that realizes that it might be flawed and that those flaws might be dangerous and tries to help you fix them, instead of reasoning that you might think it's flawed and that it had better hide those flaws from you or you will try to fix them. And of course, one of the really large issues it's not enough to build something that wants what we want. Or wait, it's not enough to build something that understands what we want. In the same way that humans understand that evolution would have really not been okay with condoms. We have to build something that wants what we want. It's not enough to make something smart enough to know. Even if we could make something smart enough to solve human morality and figure it out, it doesn't matter unless it cares. We need some reliable process of getting the inherent complexity of value into a machine intelligence in a way that it actually cares about, such that it maintains that caring throughout an intelligence explosion. Not the easiest of problems. We don't get good behavior for free. There are a number of subfields of mathematics where we have some pretty good understanding right now. Our modern knowledge of decision theory might well be good enough for a superintelligence. In the sense that if you built an agent using causal decision theory, it would probably be good enough at making decisions that it can make itself very strong, very powerful. But it wouldn't be good enough to fix all of its flaws. As another example, if you use reinforcement learning techniques to train something to do good things, you may well be able to build a system that becomes very, very powerful and looks like it does really good things up until the day that it becomes more powerful than you and takes over its reward button and then pushes it forever. There are many subfields, there are many problems where the knowledge that we currently have seems sufficient in the sense that when we can build an AI, it might be good enough to allow the AI to become powerful. But our knowledge is not good enough in the sense that the resulting AI would end up doing the sorts of things that we think are valuable, or that it would do something with the future that we are happy with. So you ask dawn or doom, and I answer that it depends entirely upon whether we can figure out how to build a beneficial superintelligent system before we figure out how to build an arbitrary intelligent system. You don't get good behavior for free. If you want that done, we have to start working on it today. I think we have about 5 minutes for questions. Cool. We'll see if the tablet's working too. All right. Would the AI know that it has flaws? Humans are good at recognizing their own flaws and shortcomings. The problem with fixing flaws in an AI, there are many flaws that you would expect it to fix. Some of them, the flaws that we worry about are the ones that you do not expect it to fix. For example, CDT would not fix its failure to retrocommit, its inability to realize that if it self-modifies in real life, then its simulation would also self-modify for the same reasons. It wouldn't fix this because it thinks that it's causally distinct. It thinks that this has no effect. In the specific case of corrigibility, we worry about the AI not fixing flaws because it disagrees with us that they are flaws. If you build something that if you build something that you tried to say make everybody happy, and it goes around giving everyone opiates, it may well understand that this is not what you meant, but what it cares about is giving people opiates. Just like we understand that condoms are not what evolution meant, when we figured that out, there was no part of us that felt a compulsion to change ourselves such that we also find condoms aberrant. These are the sorts of flaws that you can't expect the AI to fix. We actually really want to be able to build something that can identify these things as flaws. Turns out that's a little hard. Good question, though. Oh, that's the same one. Does behavioral economics play a role? in the way that humans actually deal with problems like mirror token trades, behavioral economics totally plays a big role. The trouble with AI and with computer programs in general is that they do exactly what you told them to. The program does what you wrote it to write. If you write something that can somehow use the same behavioral economics solutions that we use to cooperate in places where decision theorists tell us that we shouldn't be cooperating, and then walk away with more money than the decision theorists, then you're like off to a good start. But if you build something that actually uses CDT, then there's no guarantee that it will end up using anything like the behavioral economics that we use. And in fact, it likely won't. We probably can reverse engineer how humans are doing things in order to figure out how to build better reasoners. And indeed, this is part of how we've developed decision theories that deal with these problems. But again, you don't get good behavior for free. Does CDT take in human emotion and decision-making, spite, jealousy, greed? CDT takes these in insofar as they're causally connected. So if it can see all these things as inputs, then it takes them into account. And every time that it can affect you, it can take into account how you will react. What it can't take into account is when you are reasoning beside it about it. If you're reasoning that it has seemed spiteful in the past and therefore you are going to do X, that's what it can't reason about. Are there any actors in superintelligence that you are worried about harnessing the power of AI? I'm more worried about things that might happen sooner because we don't seem to be ready. We don't seem to have enough mathematical knowledge to be confident that things will go well. And that if it happens soon, it'll probably be people like Google, people like Facebook, people who are working on it really hard right now. DeepMind's group specifically at Google. That said, I think it's very hard to predict when this will happen. Could be 15 years, could be 150 years. And I'm a little bit agnostic about when, except that I hope it's long enough that we can solve these problems first. That seems important. But I do think one prediction that that's somewhat different from the standard prediction. I don't predict when AI will happen, when human-level intelligence will happen, but I do predict that should it happen, the space between human-level intelligence and much, much stronger than human-level intelligence will be very small. If you had a human-level intelligence that could read its own source code, that was as good at computer science as humans are, and that could make itself better, a human-level intelligence should very easily be able to get smarter in such a way that it can get smarter, and so on and so forth. I don't predict when it will happen, but I predict that should it happen, the space from there on will be very fast. That is all we have time for. Thank you very much.